Hello everyone, I am Lucas Vasconcelos, Assistant Professor at the University of South Carolina. My presentation is titled Preservice Teaches Eye Movements and Cognitive Strategies During Debugging, and this is the result of a collaboration with Dr. Arslan Ari and Dr. Fatih Ari, both Assistant Professors at the University of South Carolina. There is an increasing need for workforce proficient in coding and computing technologies. However, little research has been done as professional learning on programming for early pre-service teachers within teacher preparation programs. Professional learning should foster the use of computer science concepts and computational thinking practices such as debugging. Debugging is the process of locating errors in a program and using problem-solving strategies to fix those errors. Debugging involves systematic and thoughtful processes that involves hypothesis testing and revision until the cause of the problem is located and fixed. While debugging is very important for programming, and it is an inherent part of programming, explicit training on debugging strategies is rarely featured in computer science instruction. Programming and debugging fosters cross-cutting concepts and skills such as abstraction, conditional logic, and pattern identification. So debugging could easily be integrated into K-12 education. Studies with pre-service teachers are lacking, and the few that exist have found that pre-service teachers struggle to systematically form and test hypotheses or debug errors and explain the cause of the error. And in another study, pre-service teachers were found to simplify the program by removing a problematic area because they were not able to debug it, and they wanted to avoid problem solving. This points to the fact that further training on debugging and further studies on cognitive strategies while debugging are needed. Eye movements have been used to assess learners' problem-solving processes objectively, while learners try to understand and debug programming errors. Research on eye tracking in programming instruction is mostly focused on program comprehension and debugging. Lin et al. Found that novice learners followed a linear line-by-line program approach to debug programs, whereas those with prior programming experience followed a more logical, strategic approach as they focused specifically on the problematic area that needed to be debugged. In another study, Bednarik found that novices' eye transitions between the code and the output areas on the screen while the experts exhibited systematic eye transitions between the code and the output with more focused attention. So after a review of the literature, it was possible to find that most research in higher education focuses on individuals within computer science fields and individuals using text-based programming. So to our knowledge, this present study is the first attempt to use eye tracking or eye movement data to understand pre-service teachers' cognitive processes while they debug block-based programs. So the purpose of the study was to examine how early childhood pre-service teachers used cognitive strategies while debugging block-based programs using eye movement data and cued retrospective reporting. And that's the research question. What cognitive strategies do early childhood pre-service teachers use during debugging block-based programs? This was a mixed methods case study, and we used qualitative and quantitative data to provide an in-depth understanding of the cognitive processes during debugging. Qualitative data was collected as cued retrospective reporting transcripts, and quantitative data were eye movements. These two types of data were concurrently collected, and they had equivalent weight in this study. Participants were recruited from two sections of a course on early childhood math teaching at a large southeastern university in the United States. Convenience sampling was used. Only 2 participants, one from each course section, accepted to join the study. And both participants were 21-year-old female Preservice teachers in their senior year, pursuing a bachelor's degree in early childhood education. One participant was Mila, who was white, and the second participant was Amy, who was African American. And both participants reported no prior experience with text or block-based programming. So after recruitment and informed consent was collected, participants attended a 2-hour workshop where they practiced coding and debugging in Scratch. After the workshop, they were invited for a one-on-one debugging session, which started by eye calibration, which involved adjusting the Tobii X3120 to the shape of participants' eyes. The Tobii is a mobile eye tracker that attaches to the bottom of a computer screen, and it captures the participants' eye transitions and gaze on the screen. After the calibration, they completed 2 debugging activities where they independently find and fix errors in a faulty code that is provided to them. And finally, there is retrospective reporting. A researcher showed the participants their eye movements, their video recorded eye movements, and asked them to explain their thought processes and as the debugging strategies. One of the examples of the debugging activity is Lucia would like the cat to move following a rectangle path though the code that she put together is not working. Let's help Lucia fix the code. On the right of the slide, you can see that there is the cat representing the output of the faulty code, and the purpose is for the cat to draw a rectangle. And on the left side, there is the faulty code. And to do that, participants just had to move the 100 steps block within the repeat block and then change the second move steps to 50 so that they could form a rectangle. For data collection, we had 3 sources. The first is 3 instruments. The first is the prior knowledge test, which consists of a 12-item test on knowledge of block functions, which was administered on a 5-point Likert scale which ranged from I don't know at all to I know very well. This same prior knowledge test was adapted from Moreno and Mayer, and it focused on the names and functions of every block used in the debugging activities. The eye tracker, which recorded the eye movements while participants worked on debugging activities, and the cued retrospective reporting, where participants watched their recorded eye movements and verbalized what they were thinking, as well as their problem-solving strategies. Question prompts were adopted from Van Gogh et al. 2005, such as, where in the screen did you look to fix the error? Did you find the cause of the error? And what are you looking at now, and why? As data sources, this is the table alignment between data sources and data analysis methods. The quantitative data collected with the eye tracker consisted of 3 metrics: the total fixation duration, which is how long a participant looks at an area of interest on the screen; the total fixation count, which is the number of times the participant looks at that area of interest; and the transition between the areas of interest. And we use two areas of interest transitions: the script output and the block palette output transitions. As qualitative data, we used researchers' notes as the researcher took notes during the retrospective reporting, transcripts of the participants' responses to question prompts during retrospective reporting, and heat maps, which are generated with the Tobii Pro Studio and they show areas of the screen where the participants gaze at the most. And the quantitative data was analyzed with Tobii Pro Studio. This is what the screen looked like. You can see that there are 8 areas for 8 colorful areas. Each one of them represents one area of interest. Now let's go to the results. So this quantitative table shows the durations and the fixation duration, the fixation count per participant and for each debugging activity. So as you can see, Mila's eye gaze focused mostly on the output and scripts areas of interest for both debugging activities, while Amy focused on the output and scripts, but she also focused on the blocks palette, significantly more than Mila. When it comes to transitions, it was noticeable that there were a lot more script output transitions in both debugging activities for both participants. Now, the qualitative themes. 7 themes emerged from this study. First is that frequent and continuous eye fixation on output for a hypothesis generation. So the participants ran the code multiple times to craft a hypothesis or an idea. Then they reviewed the program, and then they tried to interpret the output to generate a hypothesis. Like Mila said, she was trying to see why the cat was not stopping, and then she really didn't know where to go. So she just kept watching it to see what the cat was doing. The second theme, simultaneous output visualization and top-down block review. So the participants simultaneously observed the output and performed a top-down analysis of the block sequence. And there was a higher number of script output transitions compared to block palette script transitions. As Emily said, she reviewed the code from top to bottom, looking at everything, and then pressed play, looking at every step, meaning that she was looking at every block and trying to associate it with the output. Third theme, eye fixations and debugging targeted the bottom of a block sequence. Debugging often entailed adding or removing blocks at the bottom of the code where the participant's eye gaze was focused. Like Amy said, the most important stuff is usually up top, which means that she suggests that bugs occur towards the end of a code sequence. And the last theme, eye fixation on faulty block, occurred if participants had a hypothesis. Participants were strategic about reviewing a faulty code only if they had a hypothesis for fixing the error. Like Mila said, the repeat part, which was the block, was throwing her off because there were 2 repeats. So she had a hypothesis, and therefore she tried to identify a faulty block. Next theme, the random eye movements on the screen were indicative of random trial and error. So as Mila was asked why she was looking randomly at different areas on the screen, and she just said that she was trying to debug, and what helped her during the process was a little bit of luck. Recognizing a key block helps narrow down the area to be debugged, so participants used cues in the output to identify the faulty block area. So for example, they reviewed the output, and then they associated the fun speech bubble with the block say fun for 2 seconds. And that was the beacon they used to narrow down more or less the area to be debugged. And the last theme is that eye fixation relied more on the block palette when participants understood the program, meaning that there were more attempts to debug the code, and therefore higher fixations on the block palette only when participants knew what the block was for, how it was to be used. So moving forward to the discussion and conclusions. So this study found that participants' eye fixation relied mostly on the output and scripts, and therefore there were more script output eye transitions. In a different study, Metnurek found that novice programmers reviewed output first to form hypotheses, while more experienced programmers used only the scripts or a combination of output and scripts. On the other hand, in another study, it was found that expert programmers switch more between scripts and program more often than novices. This study also found that participants had more script output transitions as they attempted to simultaneously review output and script to understand the program, and participants primarily fixated on the output as an attempt to form hypotheses, although they admitted that they failed at forming any hypotheses at all sometimes. So, in the related literature, a study on Scratch found that those who spent more time reviewing scripts showed more learning gains compared to others who focused mostly on the output or characters from the output. It was also found that frequent eye movements between the scripts and the output is considered typical behavior or hypothesis testing, as one modifies the program and refers to the output to evaluate it and try to understand its impact. The present study found that participants often engaged in random trial and error, which was evident in random eye movements. Participants would only review the block palette area of interest if they had a hypothesis and understood the scripts, and participants were not sure of the cause of the error even when they correctly completed the debugging task. The literature shows that trial and error is repeatedly used by novice programmers. Creating a hypothesis before debugging is typical of experienced programmers, which novice programmers don't often do. And studies with pre-service teachers found that those who coded robots often relied on trial and error to debug issues in the code, and they lacked persistence on error debugging, meaning that they would often give up on the debugging task or simplify the program. This study also found that participants tried to read the code from the top to bottom to try to understand it, but they also used beacons to try to locate the faulty part of the code, and that debugging focused on the bottom area of the code sequence. Other studies find that line-by-line, top-down approach to understand and debug the code is typical of novice learners. Expert programmers often search and locate beacons, which are defined in the computer science literature as a structure, a statement, or an operation that aid programmers in debugging. This study had several limitations, which also can be used to inform future research. So first, this study had only two participants. It was a case study. So we recommend follow-up studies on cognitive strategies during debugging block-based programs that use larger populations of early childhood pre-service teachers. Participants in this study still had limited knowledge about Scratch and coding even after the 2-hour workshop. So we recommend to extend the duration and content of the workshop so that the participants develop a deep conceptual understanding of the code and its functions before they move forward to debugging tasks. The third limitation is that both participants were novice learners. So future studies could compare the cognitive strategies used by novice and more experienced pre-service teachers based on their experience with block-based coding. And finally, participants debugged errors individually, but it's been seen in the literature that pair debugging is often useful to and pair programming and pair debugging. So future studies could examine cognitive strategies and examine pairs debugging using interaction analysis and compare differences in their eye movements. So this study was published in the Journal of Childhood Education and Society. This is the link in the reference. You're welcome to look it up and read more about our study. And if you have any questions, let us know, or feel free to email me. Thank you.